very pleased to introduce my friend, Dr. Davood Bakhshesh, who is associate professor at University of Bojnur in Iran. Davood is very good in graph theory and also in computer science. And he wants to talk about coalition in graph and coalition graphs. Davood, please start.
Hello, everybody. The topic of my presentation is coalition in graphs and coalition graphs. First, we have a presentation overview. Here are the general points of the speech. We'll begin by discussing the concept of the dominating set. Then we move on the coalition partition, followed by coalition graphs, types of coalition graphs, and then types of coalition. And especially we study total coalition. And finally, we close our presentation with open problems. Okay, the first definition is dominating set. Consider graph G with vertex set V, a simple line-directed graph. A subset D is called a dominating set for G if every vertex outside of D is adjacent to at least one vertex in D. The size of a dominating set with the minimum number of elements is called the domination number and denoted by gamma G. You can see an example for the dominating set. In this example, you see a graph in which three vertices are indicated by circles surrounding each of them. It is easy to see that these three vertices form a set of dominating set for the graph. And as another example, you can see a cycle with 10 vertices. Vertices is V1, V2, dots V10. And you can find a dominating set. As you see, these four vertices form a dominating set. As you see, the vertex V2 is dominating vertex V3, and vertex V5 dominates the vertices V4 and V6, and the vertex V8 dominates V7 and V9, and finally the vertex V1 dominates the vertex V10. And we can see that the domination number of this graph is 4. Okay, we have the definition of coalition. I don't know if my internet is connected or not. I check it. Okay.
Everything is okay, yes.
Thank you. Now we have the definition of coalition. In 2020, Heinz and others introduced the concept of coalition in graphs. Consider a graph G with vertex set V and H set E. A coalition in G is a pair of disjoint subset V1 and V2 such that these two conditions holds. Neither V1 nor V2 is a dominating set for G, and the union of V1 and V2 is a dominating set for G. We can see an example of coalition. Consider the path P9. You can see here two sets. One set contains 4 vertices determined with yellow region, and a set with 3 vertices with blue color. You can easily check that these two conditions. Each of these set is not a dominating set, but we can easily see that the union of these two sets is a dominating set. Then these sets forms a coalition. As another example, consider this graph. In this graph, we determine two sets. One set contains 2 vertices, and another set is a singleton set, or contains 1 vertex. You can see that the set with 1 vertex determined with the blue color is a dominating set, but uh, the set with two vertices is not a dominating set, and this contradicts the first condition. Then these two sets do not form a coalition in the graph. Okay, what is coalition partition? Let P be a partition on the vertex set V of graph G. The partition P is called the coalition partition if each set Vi in P is either a single vertex dominating set, or there exists another set Vj such that Vi and Vj can form a coalition. Here, single vertex dominating set is a vertex that dominates all of the vertices of the graph. Again, if each set Vi in P is each set Vi in P is either a single vertex dominating set, or there exists another set Vj such that Vi and Vj can form a coalition. And the size of a coalition partition with the maximum cardinality is called the coalition number of graph, denoted by Cg. Now there is an example of coalition partition. Again, you can see P9 here, the path P9 with vertices named by A, B, C, D, E, F, G, H, I, and we determine a partition with five elements: V1, V2, V3, V4, and V5. And you can see V1 and V2 has 3 elements, and V3, V4, and V5 are singleton set. And we can easily check that this partition is a coalition partition. For example, you can see that V1, that is A, F, and H, forms a coalition with V3 and VD, which you can check it. For example, AFH is not a dominating set, and V3C is not a dominating set, but the union of V1 and V3 is a dominating set, AFH and C. Forms a dominating set for P9. Okay, as another example for coalition partition, consider the complete graph K5 you can see that every vertex of this graph is a dominating vertex. Then the only coalition partition for this graph is the partition as we determine here contains 5 elements, and every element is a singleton. Okay, there are some results on this scope. Heinz and others in their paper entitled by Introduction to Coalition in Graphs presented some elementary result. They proved that every graph has a coalition partition, and every pass Pn, and for every pass Pn, the coalition number is equal to n if n is less than or equal 4, and if n is equal to 5, the coalition number is equal 4. And when n between is 6 and 9, the coalition number is 5, and for other values, the coalition number is 6. Also, they found same result for Cn. They proved that the coalition number of Cn is equal to n if n is at mass 6, and if n is equal to 7, the coalition number is 5, and for other values, the coalition number is 6. As you compare this, you can see that the coalition number of Cn and Pn is at most 6. Okay, some other results. For any graph G of order n, Cg is equal 1 if and only if G is equal to complex graph K1, and Cg is equal to if and only if G is equal K2 or G is equal to complement of K2. And if G is an isolate-free graph is a graph without isolated vertices. If G is an isolate-free graph, then Cg is equal to 3 if and only if G is equal K3 or G is equal the star with n minus 1 leaves. Okay, one of the important topics in theoretical studies is examining the algorithmic complexity of a problem. Based on the latest information available, the algorithmic complexity of computing the coalition number of a graph has not been investigated yet. Then we can say that the problem is still open. However, it seems that this problem, I guess, this problem is NP hard, uh, but for some classes of graphs, polynomial time algorithm can be provided. For example, according to the results presented by Heinz and others, we can easily find find a polynomial time algorithm that determine if coalition number of a graph G is at most 3 or not. Uh, Another open problem which posed by Heinz and others is that is there a polynomial time algorithm to test for a given graph G Cg is equal 4. In the next slide we will discuss about this problem, but this problem is still open. And as another open problem is that for which graph G it holds that Cg is equal to 4. In other words, characterize all graphs G with Cg is equal to 4. Heinz and other in their paper entitled by Introduction to Coalition in Graphs, they posed this problem for which graph G, or in other words, characterize all graphs G with CG is equal n. Characterize all graphs G with CG is equal to n. All graphs G of order n. In this paper, the problem partially solved for graphs G with delta G is equal to small delta G is equal to 0 or delta G is equal 1. Now we will discuss about this result. We will first we consider the graphs G with delta G is equal 0. The first result is that if G is a graph of order n with delta G, small delta G is equal to 0, then CG is equal n if and only if G is isomorphic with union of K1 and Kn minus 1. Now we will present the proof of this result. We prove the general concept of this proof. You can see here the proof. The first side of the proof is clear. The proof of C union of K1 and Kn minus 1 is equal to n is clear. We prove the converse. You can suppose that G is the graph with delta G is equal to 0 and CG is equal to n. Then, according to this assumption, a coalition partition for G consists of singleton sets V for each vertex V in G. And since delta G is equal to 0, then we can assume that an isolated vertex of G, let X be an isolated vertex of G. Since V has no neighbor in G, then for each vertex V in V minus X, the set V and set X form a coalition. This implies that the set V minus X is a clique of size n minus 1. Then we conclude that G is isomorphic to K1, union of K1 and Kn minus 1. Okay, this proof was for graphs with delta G, small delta G is equal to 0. Now we present the result for graphs with delta G is equal to 1. Before this, we provide a family of graphs denoted by F. The family F contains all graphs G that is constructed as follows. I described the construction on this figure. All graphs G in this construction contains the vertices X, Y, W, and the vertex set P and the vertex set Q. Now for the construction, first we connect X to Y, and X is a leaf. Then we connect the vertex Y to all vertices in Q, and then we connect the vertex W to all vertices in P and Q. Then we connect each vertex of P to all vertices inside P and Q. For the vertex set Q, if Q is not equal to empty, we add an edges between vertices in Q. We ensure that GQ, the graph on Q, does not contain a full vertex. A full vertex is a vertex which is a dominating set vertex. We ensure that GQ does not contain a full vertex, and each vertex Q in Q is not adjacent to at least one other vertex in Q minus Q. Optionally, we add an edges between Y and P. This completes the construction of the graph G, and we add G into the family graph Okay, according to this construction, we prove that it has been proved that if G is a graph of order n with delta G is equal to 1 and with no full vertex, then CG is equal to n if and only if G is in F. Okay, now we presented some result about the trees. We characterize the trees. All trees T with C with coalition number is equal n and is order of T, and trees with coalition number is equal to n minus 1. The result is that for any tree T of order n, Ct is equal n if and only if T is a path of order at mass 4. And also we prove that for any tree T of order n, Ct is equal to n minus 1 if and only if he belongs to the family of four graphs K1, the star with the star K1 tree, and the passes P5 and P6, and the tree S21, which is depicted here, S21. Okay, uh, there are some lower bound and upper bound on the coalition number of graphs. The first lower bound is that if G is an isolate free graph and with no universal vertex, a dominating a universal vertex is same as the full vertex or a dominating vertex. If G is an isolate free graph and with no universal vertex, then the coalition number of G is at least 4. This result presented in the paper entitled by Introduction to Coalition in Graphs. We can easily see that this lower one is sharp, this one is sharp. For example, the coalition number of the path P5 is 4. And there are another lower one using the minimum degree. If G is a graph with no universal vertex and small delta G is at least 1, then the coalition number of G is at least 2 plus delta G. Now, we will present the proof of this result. We, we, we present the general concept of the proof. To prove this result, consider a vertex V with degree is equal to small delta G, and suppose that the vertices V1, V2, V3 dots Vk are the neighbors of V. Okay, and suppose that V prime is equal to V minus NV, where NV is the set of all neighbors of V with union with the vertex V. Now, the key point in this proof is that we prove that P is a coalition partition. Consider this partition contains this set V1, V2, Vk, and finally V minus NV. You can see that in this proof we assume that K is equal to delta G. You can see that the number of the cardinality of this this partition or coalition partition is equal to K plus 2. And in the paper Hines and others prove that this partition is a coalition partition, and according their proof, it is easy to see that CG is equal to 2 plus and K is equal to delta G, then CG is at least 2 plus delta G. Now, in this result, delta G is at least 1. Now, suppose that delta G is at least 3. Then, according to this result, CG is at least 5. Is at least 5. Then remember the open problem for characterizing all graphs G with CG is equal 4. Then to answer this open problem, we must search these graphs among all graphs G with delta G is less than or equal to, but the problem is still open. I don't know how to solve this problem. Okay, for upper bounds, Heinz and others in the paper titled by Upper Bounds on the Coalition Number provide the sum upper bound. For any graph G, they prove that it holds that the coalition number of G is at once big delta G plus 3 power of 2 over 4. And if delta G, small delta G, is less than big delta over 2, then CG is at mass the multiply of delta G plus 1 and delta G minus delta plus 2. Now, in this formula, suppose that G is a 3. Since the delta, small delta for 3 is equal to 1, then we obtain this result. CT, the coalition number of 3, is at mass 2 delta T plus 2. It is an interesting problem. We characterize all trees T with CT is exactly equal to 2 delta plus 2. And this problem is open. Okay. Coalition graphs. I will talk about coalition graphs. I checked the internet. Okay. Coalition graphs. Based on the definition of coalition partitions, the coalition graphs are defined. Suppose that we have a coalition partition P with elements V1, V2, and Vk of G. Now, according to this assumption, a coalition graph denoted by CG of G and P is associated on P such that there is a one-to-one correspondence between its vertices and the members of P, where two vertices of CG of G and P are adjacent if and only if the corresponding sets form a coalition in G. For example, consider again the path P9. The vertices are X, Y, Z, W, P, Q, R, S, and T. In the please see the left side. You can see that the partition P contains 5 elements: YRT, XQS, Z, W, and P. And we can easily check that this partition is a coalition partition according to the definition of coalition and coalition partition. And please look at the right side of the picture, you can see the coalition partners in this partition. For example, consider the XQS, X in the set XQS. XQS forms a coalition with Z and with W. We can check it easily. And also the set YRT forms a coalition with W and with P. And we can check that there is no coalition between these set. For example, there is no coalition between XQS and YRT. Um, okay, you see a graph, and this graph is isomorphic to this graph. In the bottom of the slide, this graph is P5, past P5. Then we say that the P5 is a coalition graph of P9 related to coalition partition P. As another example, consider the star with with 5 leaves. Here you can see that uh, a partition with 3 elements: V1, V2, and V3. And you can see that V3 is a singleton set, and V1 have 2 vertices, V2 have 3 vertices. And you can see that V3, since is a dominating set vertex, V3 has no coalition with one and with V1 and V2. But V1 and V2 has a coalition, form a coalition. In the right side figure, you can see that the graph related to this coalition partition. V1 forms a coalition with V2, but V3 has no coalition with them because V3 is a dominating set. Then in the bottom of this slide, you can see that this graph is isomorphic to K1 union of K1 and K2. Then we can say that K union of K1 and K2 is a coalition graph of this star graph related to this partition. Now, Hines and others in the paper Coalition Graphs of Passes, Cycles, and Trees showed that if P is a coalition partition for a pass PK, then the coalition graph of PK and P belongs to the family F. This family is different with in the family F that I introduced in the previous slide. F is a family of graph contains 18 graphs. K1, K2, complement of K2, as you see here. Uh, okay, Heinz and others, after this problem presenting this result, posed the following open problem: how many coalition graphs are defined by coalition partition of any pass PK? They call any coalition graph of pass PK by CP graph. CP graph is the coalition graph of passes. Uh, in this paper, we prove that this problem, uh, and we find the CP graph of PK. To prove to solve this problem, we first find this table. In this table, we use letters Y and N, uppercase letters and lowercase letters Y and N. Suppose that T, I, J in in tree I and J. Tij be the cell of the table in the row I and column J. Let CPI be the CP graph, coalition graph of paths. CP graph in the row I, and let PJ be the path in column J. When Tij is equal to uppercase letter, it means that using some corollary proposition Lemma theorem, we have obtained the value of Tij. And when Tij is equal to a lowercase letters, it means that we empirically using computer programs obtain it. If Tij is equal to y uppercase or lettercase, it means that the CP graph CPI can be defined by the path PJ. And if Tij is equal to n uppercase or lettercase, it means that the CP graph CPI cannot be defined by the path Pj. According to this table, we obtain this result. Let NCPJ be the number of coalition graphs of Pj defined by its coalition partition. We show that NCP1 is equal to NCP2 is equal to 1, and NCP3 is equal to 2, NCP4 is equal to 3, and NCP5 is equal to 6, and NCP6 is equal to 10, NCP7 is equal to NCP8 is equal to 12, and NCP9 is equal to 14. And finally, for any integer k with k is at least 10, we prove that NCPk is equal to 15. Okay, there is an problem for Heinz and others answer this problem for any treaty and a coalition partition P1T. What is the structure of coalition graph? As you see in the previous slide, we discussed about the passes, but here is a general result on tree. What is the structure of the coalition graph of trees? Heinz and others prove that the coalition graph of trees is belongs to this family K1, K2, complement of K2, union of K1 and K2, P3, K3, and any spanning subgraph of K2 plus Kn minus 2. Okay, here we will discuss about the types of coalition graphs. Heinz and others in their paper entitled by Coalition Graphs introduced some types of coalition graphs. The types of coalition graph are singleton coalition graphs, self-coalition graphs, complementary coalition graphs. Here we will define these graphs. What is singleton coalition graph? First, we have the definition of singleton coalition partition. A singleton coalition partition is a coalition partition denoted by P1 of a graph such that every member of this partition is singleton. And a coalition graph obtained from this singleton coalition partition P1 of graph is called the singleton coalition graph or SC graph, denoted by SC graph of G. For example, consider the cycle C4 in the left side of the picture. A, B, C, D are the vertices of cycle, and you can see that P1 is a coalition partition for C4 and contains four vertices. And you can see the coalition graph of the C4 associated for P1, and you can see that, for example, the set A forms a coalition with B, D, and C. In general, every set of this partition forms a coalition with other set of this partition. And finally, we conclude that the coalition graph of this graph with this partition is the graph K4. Since this partition is a singleton, then K4 is a SC graph of C4 or singleton coalition graph of C4. And we write this result with C4 and right arrow K4. It means that K4 is a singleton coalition graph of C4. One can ask a question: uh, uh, what is the graph after K4 in this chain? We can easily see that the singleton coalition graph of K4 is the complement of K4. It means that the complement of K4 is the singleton coalition graph of K4. And one can ask another question: what is the end of this chain? Um, mm, Fortunately, the end of this chain is the complement of K4. It is remarkable that the complement of K4 has not singleton coalition partition because the complement of K4 has exactly four singleton vertices. Okay, one can find some important result on the singleton coalition graph chains in our paper titled by Singleton Coalition Graph Chains. What is the self-coalition graphs? Let the self-coalition graph is defined based on the singleton coalition graph. Let H be the singleton coalition graph of graph G if H is symmetric with is isomorphic with G, then G is called a self-coalition graph. For example, C5 is a self-coalition graph. Then in this chain, if we insert C5, we have C5, then C5, C5, C5. As in C5 then C5 is a self-coalition. And for more results, see the paper by Hans and others entitled by Self-Coalition Graphs. And what is the complementary coalition graphs? Let H be the singleton coalition graph of the graph G. If H is isomorphic to complement of G, then G is called a complementary coalition graph. For example, you can see that P3 is a complementary coalition graph because the singleton coalition graph of P3 is the graph union of K1 and K2. For more results, see the paper Complementary Coalition Graphs Characterization and Algorithm. Okay, in the previous slide, we discussed about the original definition of coalition. There are another type of coalition: total coalition, connected coalition, independent coalition, and edge coalition. You can see some research work on these types of coalition. We especially discuss about the total coalition. The total coalition is based on the definition of total dominating set. A set D subset V is called a total dominating set for G if every vertex in V is adjacent to at least one vertex in D. And the size of a total dominating set for G, denoted by gamma TG, is the minimum number of members required. For example, you can see a total dominating set. You can check it. The vertices with yellow color forms a total dominating set. Okay, according to this definition, total coalition is defined. Total coalition introduced in the paper entitled by Total Coalition Graph located in archive. A total coalition in a graph G consists of two disjoint sets AY, A1 and A2 of vertices G, neither of which is a total dominating set, but whose union is a total dominating set of G. And according to the definition of total coalition, a total coalition partition is defined a vertex partition epsilon with members A1, A2, dots AK is called the total coalition partition if its set AI forms a total coalition with another set AG. But no set of epsilon is a total dominating set. The total coalition number of G denoted by CD refers to the largest possible number of members in a total coalition partition of G. Similar to the definition of coalition graph, the total coalition graph is defined. Okay, here you can see an example of total coalition partition. Consider the path P6. The vertices are A, B, C, D, E, F, and you can see that epsilon with members A, B, D, E, F, and C forms a total coalition partition. We can easily check that. For example, the set B, D, F forms a total coalition with C and D. And uh, in this in the bottom of this slide you can see that another partition on the P6, but this partition is a coalition partition and is not a total coalition partition. You can see you can easily check that this partition is a coalition partition and this partition is not a total coalition partition because the member C has no total coalition partner. We cannot find a partner for C. And there is a lower bound in the paper titled Total Coalition Graph. The authors prove that for any graph G that does not contain any isolated vertices and full vertices, then the total coalition number of G is at least small delta G plus 1, and this bond is sharp. And for trees, there is a result. If T is a tree, then the total coalition number of trees is at most big delta T plus 1. To prove this result, here is the general concept of the proof. We first proved that total coalition graph of the total coalition partition of T is symmetric to a star with delta leaves, and according to this result, we can easily prove that the number of vertices this star is big delta T plus 1, and a result for graphs for graphs G with delta G is equal to, if G is a graph with delta G is equal to, then the total coalition number of G is at most 2 delta G. And you can see a general concept of the proof here. For the proof, we prove that the corresponding total coalition graph is symmetric to the one of the following graphs. In these graphs, the black vertices are leaves, and in this graph you can see that there are at most in every graph you can see that there are at most two red color vertices, and there are exactly one blue vertices. Then we prove that the degree of any red color vertex of this graph is big delta G. Then according to this, we prove that the total coalition number of G is at most 2 delta G. Okay, in the last slide, we will present some open problems. The first open problem is the decision problem related to the coalition number in hard. There is no result on this scope. I think it is an interesting problem to work. Researcher works on this. I guess this problem is NP hard. And another problem is that is there a polynomial time algorithm to determine if coalition graph G is equal 4 or not? Coalition number is equal to 4 or not? For solve this problem, I think we must search according to this slide. According to this slide, we must zoom on the graphs with delta G at most 2. And another open problem is that characterize all trees T of order n with coalition number is equal to n minus k for a given integer k, where k is between 2 and n minus 2. In this presentation, we will discuss about the coalition number of trees when k is equal to 0 and equal 1. In this problem is for integer k, where k between 2 and n minus 2. And finally, is there a polynomial time algorithm to determine the coalition number of a tree T? Thank you very much. Please, any question?
Okay, thank you so much, Davood, for your nice presentation. Is there any question or remarks, notes? Hamid,
Davood, thank you very much.
you have a question, Hamid.
Professor Ali Khani, I think that this is a good time to take a photo for a memorial, because the last invited speaker, who is Paul Darbeck from France, joined us. And dear R, please turn on your webcam to take a photo for a memorial.
Okay, first,
please take a photo for a memorial.
Okay. If there is no question for Davood, please thank again Davood. Thank you so much, Davood, for accepting the invitation of this workshop.